Hi, so let's begin. Please welcome Ben Darnell.
All right, thank you everyone. My name is Ben Darnell. I'm the co-founder and chief architect of Cockroach Labs, makers of CockroachDB. And I'm here to talk today about database isolation levels and how to think about them without the anomaly table that appears in most database documentation. First of all, what is CockroachDB? We are a company building a database built from the ground up to meet the needs of today's data-driven world in the cloud. So we're combining the consistent transactional support of a relational SQL database with the scalability and flexible deployments of a non-SQL database and bringing it all to the cloud in a managed environment that can auto-scale up and down from zero. So we're bringing all of this with a mostly Postgres compatible interface so that it's very easy to plug your applications into CockroachDB and getting the benefits of strong consistency and isolation in a scalable database in the cloud. I'm not going to talk about CockroachDB today. I'm going to talk about database isolation levels. This is a concept that appears in every database from Postgres to Oracle to SQL Server, but a lot of people don't really understand them. And so I'm going to talk about what isolation levels are, kind of the traditional ways of thinking about them, and then how I like to think about it, focusing on how isolation levels affect the way you write your application code. We'll talk about some of the ways that these isolation levels can be implemented differently between different databases, including in particular Postgres and CockroachDB, but I'll also touch on a few other names you might have heard of, and wrap up with some practical guidance on how to choose the right isolation level for your application. So, what are isolation levels and data anomalies? Well, if you look up, if you look in the SQL standard, there are 4 officially defined isolation levels: read uncommitted, read committed, repeatable read, and serializable. So what do these names mean? Well, in the SQL standard and in most database documentation, they're described with a big table that looks like this. This comes from the documentation for Postgres 16, but most databases have a very, very similar table like this, where they say that they define data anomalies: dirty read, non-repeatable read, and phantom read, and serialization anomaly. And then you define the differences between the isolation levels based on which of these anomalies are possible. So read uncommitted is the only isolation level where dirty reads are possible. Every other isolation level prevents dirty reads. Read committed isolation prevents dirty reads, but it can allow non-repeatable reads. Repeatable read, as you might imagine, allows make sure that your reads are repeatable, but it can still allow other anomalies, including phantom read. And then serializable is the gold standard of isolation level. Serializability is defined as every transaction runs as if it is the only thing running on the database at a time. Even though there may be other transactions executing concurrently, in serializable isolation, the database is required to present each transaction the appearance that it is the only thing in the database. So this is the standard way of defining isolation levels, but I find that it's not actually the most helpful way to think about it. So what's wrong with it? Well, first of all, it's incomplete. This set of isolation anomalies was kind of set in stone back at least by 1992. Since then, there's been a lot of research in the database world. We've identified new kinds of anomalies, such as right skew was identified by a group led by Hal Berenson in 1995. Atul Adya did a massive amount of work on database isolation in 1999 and identified anti-dependency cycles and other even more obscure kinds of anomalies. And along with these discoveries of new isolation levels, if you just add more columns to the matrix that I just showed you, you're going to need more rows to go with it. You're going to need more isolation levels. And so that leads to snapshot isolation, which is an isolation level that emerges from certain ways of implementing a database, or a monotonic view and consistent view, which were identified by Adya. We've also found new ways of implementing the old isolation levels. You can combine, you can extend snapshot isolation to get serializable snapshot isolation, which is equivalent in terms of isolation to the traditional serializability, but it sometimes performs differently. Some databases implement a lot of different isolation levels. SQL Server actually implements the read committed isolation level in 2 different ways. You can have locking and you can have snapshots, and there's an option to choose between these. So this gets very complicated when you start to think about isolation levels in terms of anomalies. And most importantly, no one actually thinks this way. No one thinks that my application can tolerate phantom reads but not write skew, and so I'm going to pick the repeatable read isolation level. That's the best choice for my application. What does everyone actually do? Well, realistically, they just use the default, which in most databases is read committed, and occasionally they run into a problem that will lead them to increase or decrease their isolation, usually decrease, but they don't really have a principled way of approaching it. So my framework for thinking about isolation levels is to start with the application. Because of course the databases don't exist in isolation, you're going to build some sort of application on it. And the way you write your application code is actually going to change depending on what isolation level you're using. It's actually a mistake to try and take an existing application and change the isolation level out from under it without thinking about what that means for the app itself. So let's say you're starting with a low level of isolation, like read committed. This is because this is the default for most databases. This is how most people start out. If you're running at any level of isolation below serializable, then sometimes it becomes necessary to use explicit locks called the SQL select for update or select for share clause. If you're running at an isolation level other than serializable and you're not using select for update, at least occasionally, you probably have some bugs in your application. And in concurrent situations, these missing locks can allow your transactions to incorrectly overwrite each other's data. On the other hand, having too many locks can hurt performance because the transactions start to block each other out, and that reduces your concurrency. And so it's a balancing act. You've got to try to keep your think carefully about where the locks are required so that you have enough to make your application correct, while still not doing so many that it hurts performance. So you may look at this and say, oh, well, I'd rather run at serializable and not have to worry about that. This is the philosophy that we favor in CockroachDB. Serializable was the first and default isolation level that we implemented, exactly because we think that most of the time it's not a good use of application developers' time to think about exactly where they need to add these locks for correctness. But it's not all good news. Because higher isolation levels require sometimes transactions get aborted and have to retry from the beginning. And this is something, the most straightforward way to explain this is a deadlock. If one transaction locks row A and then tries to write to row B, another transaction wrote to row B and then tries to lock row A, those transactions are in a deadlock. They can't both continue. And so the database is going to have to pick one of them to abort, and then the other is going to be allowed to continue. The one that was aborted can then try again from the beginning and see if it wins the race to get the locks that it needs. Deadlocks are actually possible in any isolation level, even read committed. And so you sometimes have to think about retries for deadlocks, but in most applications, real deadlocks end up being pretty rare. But as you go up the scale of isolation levels to repeatable read and then to serializable, there are more kinds of ways for transactions to interfere with each other, and so this problem of retriable transaction aborts and retries becomes a more severe problem. So whereas you might be content to say that, well, if a deadlock happens, then I'm just going to return an error to the user and let them reload the page, you might not be happy with that in serializability because this is much more common. And so you may feel that you need to put some sort of try-catch block in your application to catch the error and retry. And this can become extremely tedious depending on how your application is organized. So let's walk through an example in more detail. So here I have a simple transaction, kind of a toy version of a bank account transfer, written with a little Python function. And this transaction runs 3 SQL statements. We select the balance from the account to make sure that we have enough balance to make our transfer. And then we do 2 update statements to update both the from and the sender and the recipient account with the new amounts. And so we end up looking at this balance field in more than one place. So we read it from the same account in both the select statement and in one of the updates. So what happens if there's a concurrent transaction and the balance changes? What happens is going to depend on what your isolation level is. So starting with read committed, each of these statements is going to see a different value for the balance. So you may see in the first select statement that you have enough money in your account, and then another transaction comes through, and then by the time you come to the update, your balance is lower, and now it can actually become negative. And so this is probably not what you wanted because you put in this balance check. And so you need to be able to prevent this balance from going negative in the course of this transaction. And so you need to add the for update clause to the select when you're reading to ensure that the amount is going to stay the same from your select to your update. And what happens in serializability? This is a little more complicated. So if there's a concurrent change to the account balance in serializable, then you're going to get an error. The errors are often very cryptic. In Postgres, this returns an error that says, could not serialize access due to concurrent update. And this tells you that there's been some interference between transactions updating the same row, and we can't be sure that it's safe to continue, and so we're going to return an error and let you try the transaction again from the beginning. Now, you may wonder, why can't the database handle this for me? The database sees all my SQL statements. Why can't it start over and do this for me without bothering my application? The reason for this is there on right after the select statement. We run a couple of Python statements. We run a Python if statement. If the balance is lower than the transfer amount, then we return, and then we don't actually execute the update statements. This Python statement is completely invisible to the database. And so the database can't say that it's safe to continue after the update to the balance, and so it has no choice but to return an error to the application. Now, there are some ways to move more of this information into the server side. So, for example, if this was running as a stored procedure, then the database could retry it automatically. But the way most of us are writing our applications these days, we're doing a lot of back and forth between our application code and code in the database, and so the database on its own is not able to handle retries for you automatically. So I skipped straight from read committed to serializable here. And let's come back to the middle isolation level of repeatable read. The reason I skipped over it is because databases differ in how they implement repeatable read. It turns out that in most databases, this example works the same in serializable and repeatable read. You'll get an error message that contains the word serializable in it, even though you're not running a serializable, you're running a repeatable read. And this is true of Postgres, CockroachDB, Microsoft SQL Server, and Oracle. Occasionally, it works more like read committed. This is true in MySQL, and I think it's true in DB2, although I haven't been able to verify that. So repeatable read is a bit of a worst case scenario because depending on what database you're working with, you may need to add select for update to make it safe in MySQL, or you may need to add an error retry loop like you would in serializable. This depends more on your database implementation details than read committed or serializability, which are a little better defined. So where do these differences come from? Why do some databases behave differently with some isolation levels than others? Well, I want to call your attention to something that I didn't dwell on an earlier slide, but in the anomaly table in the Postgres documentation, we see that in repeatable read, the phantom read anomaly is allowed according to the SQL standard, but it's not allowed in Postgres' implementation of repeatable read. So what does this mean? SQL defines repeatable read as the isolation level that permits phantom reads and nothing else. Postgres doesn't actually permit phantom reads, but it does permit something else. It permits an anomaly called write skew. This means that repeatable read in Postgres is actually not repeatable read according to the SQL standard. It's another isolation level called snapshot isolation, which is very similar to repeatable read, but not quite the same. The reason for this difference is that there are a couple of different ways that you can implement transactions and isolation in a databases. The two basic approaches are either the locking approach. You get a shared lock on all the records you touch until the end of the transaction to make sure that no changes are allowed concurrently, or multi-versioning concurrency control, or MVCC, where the database stores multiple versions of each record. Old versions are not immediately deleted when they're overwritten, and this allows older transactions to continue to see older versions of data even as newer transactions are writing on top of them. And so repeatable read, as defined in the SQL standard in terms of phantom reads, is kind of a natural way to implement databases in this locking world. If you look at database documentation about phantom read, you'll see that they talk about things like gap locking and things like that as their solution for phantom reads. Newer databases usually use MVCC, and in MVCC, it's much more natural to implement snapshot isolation and have the risk of write skew than to implement repeatable read and have the risk of phantom reads. The SQL standard tried really hard to be implementation independent. They didn't say that you need to get locks on certain records in your isolation levels. They tried to define it in a neutral way in terms of the kinds of anomalies that you get. But they kind of missed the mark when it comes to repeatable read, because phantom read is a phenomena that is mainly relevant to locking implementations. And in multi-versioning implementations, it's more relevant to talk about write skew, and the SQL standard just doesn't mention this at all. So there's some debate about whether it's completely standards compliant to implement snapshot isolation and call it repeatable read as Postgres and a number of other databases have done. My answer to this is that repeatable read is poorly defined in the SQL standard, and that's basically fine. We've been living with this for 30 years now, and we've built applications on top of databases. They mostly work. And that says that the exact details, repeatable phantom reads and write skew, that's not the important thing. The important thing about repeatable read is that your reads are repeatable. If you do the same read twice in a repeatable read transaction, you're going to get the same results. That's really the only thing you can count on from repeatable read, and that's an important block to build on. So, having covered kind of how we came to have all these different isolation levels and what they mean, I'm going to walk back through the list of isolation levels and give you some guidance, my opinions on when each of the isolation levels is a good choice. First of all, I want to say one of the first things that people look at when they look at isolation levels is they assume that lower isolation levels are going to be faster. It's actually more complicated than that. It is true that high isolation levels have higher variance. A small fraction of your transactions are going to have to hit an error and retry, and so some of your transactions are going to take twice as long as usual. And so this is, depending on your application and how often this happens, maybe it's not going to show up in your median or mean latency. Maybe it'll show up in your P99, maybe it'll be P99.9 or 99.99, something like that. But some fraction of your retries or of your transactions are going to be slower if you're using higher isolation. But in the typical case, in the median or mean case, low isolation can be faster. It often is, but not always. In CockroachDB, we've implemented both serializable and repeatable read, and we find that the TPCC benchmark actually runs a little bit faster in serializable than it does in repeatable read. This is somewhat unusual. Most other benchmarks that we run show that repeatable read read committed is faster, sometimes by a significant margin, but at least sometimes serializability can be faster than lower isolation. And this is because CockroachDB is a distributed database, And distributed locking is more expensive than non-distributed locking, proportionally compared to everything else. And so the extra locks that you need in repeatable read committed to make your transactions correct can sometimes be more expensive in distributed database like CockroachDB than they are in non-distributed databases. The other thing to consider here is that the defaults matter, because whatever version is the default is going to be the one that gets the most concentrated optimization effort from the developers. So CockroachDB has defaulted to serializability from the beginning. We've spent a lot of time optimizing it. We have a lot of optimizations and shortcuts and heuristics in our serializability implementation that we think makes it one of the best in class for high isolation levels. Other databases haven't necessarily made that investment. So in other databases, when you start to upgrade isolation levels to serializability, you may see a bigger drop in performance than you do in CockroachDB. But that said, let's walk through the isolation levels one at a time and see where they fit. Use read uncommitted if consistency low latency is more important for your application than getting the right answer. That sounds kind of flip and dismissive, but there are times where that's a legitimate choice to make. Sometimes you'd want to get a quick answer without blocking, because even stale or dirty data could be more appropriate for your application, and it's just not worth waiting for a competing transaction to complete. This actually turns out to be more important in the locking approach to isolation implementation than in the MVCC approach. Most MVCC databases don't implement read committed. So even if you tell Postgres that I want read committed, it's just going to give you, if you tell Postgres you want read uncommitted, it's just going to give you read committed instead. It has no way for you to get the uncommitted reads. But this was important for some early implementations of locking-based databases. And even in CockroachDB, we do have one place in our code where we use read uncommitted transaction internally to avoid certain kinds of deadlocks in startup and failure recovery. Sometimes we need to peek into a pending transaction and figure out what's going on before we can pick up the pieces from a cluster that has experienced a crash. So this is occasionally useful, although it's really pretty rare. And at least one of the databases out there that does implement read uncommitted is SQL Server. But SQL Server also implements both locking and MVCC-based versions of read committed. And so in most cases, if you're using SQL Server, you're probably better off using read committed snapshot instead of read uncommitted. Up next is read committed. This is the default in most databases, including Postgres. And read committed is good because it gives you consistently low latency even at high percentiles of your query traffic. And it's a good choice if it's hard for you to catch and retry errors in your application, but it's easier for you to keep track of the explicit locking needs and to add your for update clauses where necessary. It's also, if it's the default for your database, then it's probably a good idea to stick with it instead of changing from the defaults, because your drivers and ORMs and whatever frameworks you're using are probably going to be tuned for whatever your database's default is. For repeatable read, I like to use repeatable read for read-only transactions. Because read committed transactions that are read only don't actually really do anything. Each statement in a read committed transaction is independent. They see different versions. You're not really doing anything by putting them in a transaction. So if you need to be able to read consistent data from your database across multiple statements, then you really need your transaction to be at least repeatable read, if not serializable. And if your transaction is serializable, then it can be depending on your database, it can be a little bit cheaper to run in repeatable read instead of serializable. On the other hand, as I talked about earlier, repeatable read is a little less portable than the other isolation levels. You know that reads will repeat. You can get the same data multiple times. But the exact details of how read-write transactions work in repeatable read get very messy. You may have seen, if you're a big fan of Kyle Kingsbury's Jepson posts on distributed database implementations, you may have seen recently that he did a study of MySQL's implementation of repeatable read and found all kinds of anomalies with it. So repeatable read can be a trickier isolation level to work with than either read committed or serializable. Finally, you should use serializable isolation if data accuracy really is paramount for your application. If you don't want to take the risk that any inconsistencies are coming into your data due to concurrent operations. If you want to see more about ways that this can even escalate into being security problems, there was a research paper out of Stanford a few years back called Acid Rain, which found security vulnerabilities in some 20 different applications, all relating to the use of lower isolation levels and insufficient locking. On the other hand, in order to use serializability, you do have to deal with these retry errors that can come up. And so if you are able to architect your application from the beginning to have these retry loops implemented in a centralized way, that can really go a long way to making it easier for you to use serializability. Another interesting thing that comes up sometimes is that sometimes there's another retry loop already going on in your application. If your application is backing a mobile app, then your mobile app is probably going to retry on network errors and things like that anyway. And so maybe that means that it can also use that same retry loop to handle errors from serializability in the database. Maybe you don't need to have a server-side retry loop in addition to your client-side retry loop. So, in conclusion, yeah, the details of data anomalies that are the traditional way of explaining SQL isolation levels, they're not the most important thing. Instead, pick your isolation level based on based on how they cause your application to block and how transactions interfere with each other, and how they expose retryable errors to your application. And if you have any more questions, I would be happy to talk more. You can come by our CockroachDB booth. We're back towards the entrance. We're the second booth from the entrance. Thank you very much.
Thank you, Ben. Any questions?
Hi, thanks for the talk. So you mentioned that there have been a few anomalies that have been discovered after the 92 standard. So have there been any efforts to include those in the standards, or are these like the 4 fixed anomalies?
Any interest in updating the definitions of the isolation levels, even though there's been pressure on them since 1995 when a lot of this research first started. But the SQL Standard Committee seems to be okay with the status quo, and they're not interested in redefining anything.
Thanks for the talk. So I think repeatable read with inside repeatable read, if you use select for update, it might get rid of many retries and even some of the anomalies like write skew. It might take care of. That might be the best way, or maybe one of the takeaways.
Yeah. So in repeatable read, sometimes select for update is necessary to avoid anomalies. Yes.
And another CockroachDB related question. So you said the distributed locking. So does it mean CockroachDB takes locking approach rather than the multi-version?
So CockroachDB is, sorry, I couldn't hear the last part of the question. 2PL or MVC? Yeah, so CockroachDB is MVCC based. So normally we do everything based on multi-version concurrency control with unreplicated locks held in memory on certain nodes. But in lower isolation levels, those locks, if you're getting an explicit lock with select for update, that lock actually has to be replicated in a way that it doesn't have to be in serializability, and so that's why our read committed implementation can be slower than serializable.
A quick question around, let's say you have an application you're building and you need both use case, read committed and serialized, because you might have a place of code where lots of callback coming to a single point, and you don't want to enforce a select for update because that will create a race condition. So what I tried to do is basically set the isolation level for a certain transaction and certain piece of code with a retry logic instead of making the whole database serializable. So
Yeah, so this is a complicated area because different transactions can have different isolation levels, and it's really poorly defined how transactions of different isolation levels interact with each other. But yes, it is possible to have some transactions in read committed and some in serializable, and I really have no idea how other databases handle this. We have our interpretation of the rules when transactions of different isolation levels interact, but it gets very complicated to think about very quickly if you're combining different isolation levels.
Yeah. And one more thing I want to add, like, let's say you are using read committed and you have a select for update, race condition happening, lots of threads waiting on the lock. So what I did for my experience, I usually have a lightweight locks on Redis, which is more a distributed lock. You have a single place, so you won't make your database have a big lock queue being there. So that helped me a lot in that scenario.
Yeah, you can use external locking or queuing in some cases if the database internal locking is not working the way you would like.
So I just want related to this CockroachDB is how does you take care this particularly write skew problems as or you can say it's a read write problem. Right? We say it's a read write problem. You read something and try to write something wrong information. It's called as a write skew problem or read write problem. So how do you take care? I know MBCC is the optimistic technique you use, but with MBCC, some other extra things you added to control that?
Yes, so to guard against write skew, in order to implement serializability, yes, we have to go a little beyond just the basic MVCC. So what happens, this is a very, very long conversation to go into the details, but the short version is that at the end of the transaction, when you go to commit, we go back and re-examine rows that were previously read in the transaction to see if there were any subsequent writes that would cause write skew.
Got it. Thank you.
Yeah. So while developing a new database and testing for these isolation levels, is there a benchmark test which a framework which has been designed for you to claim that okay, the database technology is working as expected for these isolation levels? So.
Yeah. Is there a standard benchmark or test for this? Not as much as you would like. We have, in the course of developing CockroachDB, we've been able to adapt parts of the test suites from both SQLite and Postgres, and so we're able to test and compare that way. But there is no, official standard SQL test suite that says this is how things should work.
So the follow-up question was like, if there is any, it can help understand the behavior of different isolation levels and make a better choice while understanding that, right? So.
Yeah, testing isolation levels is really tricky because it is inherently vulnerable to race conditions. It depends on concurrency and things like that. So it's hard to test in a portable way. I think we had one more question in the front.
Thanks for the insightful talk. I have a query regarding the anomalies that you sort of touched upon while discussing the isolation levels. So I was just wondering if you're aware that there are scenarios or people have looked at a problem outside, that means into the application in terms of invariants.
Yeah.
So, are you aware of such studies or research that's been done to attack it from this perspective?
Yeah, I mean, I think this is, you can have data anomalies coming from the application side as well. I mean, in a lot of ways, when your transaction code is distributed across the SQL that runs in the database and the code that runs in your application, then that's a broader scope of your distributed system, and there's more. You really need to consider the entire thing as a larger distributed transaction. This is where protocols like XA have come in for distributed transactions. But practically speaking, my best advice there is to try to contain your state as much as possible in one database so that everything can be managed transactionally in that scope.
If I'm not mistaken, CockroachDB is written in Go.
That's right.
And when you do that implementation, in many places you would have had to use Go routines with channels. So again, you would have had to take the same approach of enforcing invariants to deal with that anomalies when you are in a particular isolation level. So I was curious if you had something to share from experience.
It's true that we're written in Go. I'm sorry, I didn't follow the question. Maybe we can talk a little more offline. All right. Thank you.